In audio processing, the conv1d layer is useful when the entire audio signal is in memory. Then the convolution can be seen as shifting the time reversed impulse response, the weight, along the audio signal to produce the output of the convolution. But when we would like to do real-time audio processing, the audio signal arrives block by block from the sound card, and we should process them as they arrive. This can be seen as shifting the audio signal along the time reversed impulse response, the weights. We can implement this using a dense neural network layer, or fully connected layer, using a Keras dense layer. This layer has different definitions for the weights and the input, hence we need to translate them for this layer. The dense layer basically implements a matrix multiplication, where the input signal is a row vector from the left and the matrix from the right contains the weights. In our case, this matrix is a column vector. So first, let's look at the weights. So the weights, they don't have the channel dimension, hence we need to remove it. Then we need to apply the time reversal from the convolution, and we can do this using this flip. So here it's very important to understand if the library is giving back the convolution as time or a cross correlation, and then we need to see if we must time reverse or not. And then we can set up a dense neural network model, and we can use, instead of the convolution, we're using a dense, and then we have linear activation, BS equals to false, and we pass the input shape, and we have here just 1 unit. And then finally we need to transpose the input to be a row vector. Then we can loop over the signal. So here it still comes from the signal in memory, but it could also come from the sound card. So we're just simulating that the signal is coming from the sound card, and we will loop over the signal. And this is what we're going to do in this example. So it's a simple program to implement a convolutional neural network using a dense network for real-time audio applications. So here we are again importing our libraries. We will open the weights. We'll open the file containing the weights that we used before. So we see that the weights have this shape here. Now we need to convert the weights from the convolutional layer to a dense layer. So we are removing the channel dimension for these weights, and this is what we are doing here. So in this case, we don't need to do flipping the impulse response dimension from the convolution layer, because the convolution layer is already giving us the flipped weights. So now we build our model using this equation, and we are using a dense layer, fully connected layer. Here is the same old generate dummy data, so we are generating our inputs and our outputs. Here we are transposing the signal for the dense layer to obtain row vector to be multiplied from the left to the weight vector in the dense. Here we will loop over the entire signal in single steps until the end. And in each step we try to decode. And this is what we are doing, and we see again that the output of our neural network is very similar to the previous that we had here using the convolution. Now we are using this dense fully connected layers. So we're implementing a convolutional neural network using a dense network.